Good afternoon, everyone. So my name is Ruben Till. I work with the Fraunhofer FHR in Wachtberg. This is close to Bonn in Germany, and I'm going to present some work my colleague Andreas Bartelt and I did in the area of joint communication and sensing and how to add compressed sensing to it. Yes, so to our background, so we are institute mainly focused on radar research, and in radar, for instance, especially in linear frequency modulated continuous wave, you have the nice advantage that you can create chirps in the analog domain, send them out and have a very high bandwidth, which gives you a very good range resolution, and then you receive that sample, that signal back, do stretch processing, and you only have to sample the intermediate frequency to get the entire signal and the full resolution. And you can do some nice stuff with this, like for instance SAR imaging, like in the lower picture, and there's a sample image. But you not always want to deploy these kind of radar systems, or sometimes you don't have the resources, especially frequency is becoming a scarce resource. So there's the thing called joint communication and sensing, which is not new, but it's kind of new to us. And the concept is that you use, for our case, we do communication-centric joint communication and sensing, so we add some sensing capabilities to communication waveforms. In our case, multi-carrier waveforms, we could use anything like OTFS, but in this particular case, we use OFDM. And we have a monostatic setup as a beginning, and I linked some related work below, but I'm not going into that. So coming to our signal model, so we have transceiver A and a transceiver B, and transceiver A tries to communicate with B, and in the channel there are like 4 scatterers. And let's assume transceiver A also has an RX channel, and it also tries to receive its own backscattered TX signal, and that would be like just the TX signal convolved with the channel impulse response, where I just plotted the magnitude spectrums, like a sample of how it could look below. You can model it in the time domain, but also you can just take the impulse response to frequency domain and model your received signal in the frequency domain directly. So we basically have, as a received signal, the send signal, which has some phase variations due to the time delay introduced by the channel. So out of this received signal, we can create a compressed sensing problem. So we have our received vector Y, and then we have a sensing matrix, which consists of 3 components. Matrix P, which is our selection matrix, where we select our subcarriers we want to send on. Then we have our signal matrix S, where our baseband signal is in, and then we have the matrix B, which is a Fourier-like basic matrix, where we also have the phase delay put into, which is introduced by the respective subcarrier. And then we have the vector X, which is our scenario we want to see. So those are our range samples, basically. It's a grid, and we just assume that we only have a few non-zero components there, so only a few scatterers in there, and the rest of the signal is then buried in noise. And then we have an underdetermined system which we can solve with compressed sensing. In this particular case, we have an OMP-based method like orthogonal matching per seat. And to give you an intuition of what we want to do, so like as I already said initially, our resolution is related to the bandwidth we have. So the higher the bandwidth, the better the resolution. But in communication, you don't want to use the entire bandwidth just to do some sensing, because you would be denying the spectrum to other users within there which also want to use it. So our scheme is to randomly select carriers across the available frame and synthesize that together so we get the full resolution we would have using the entire bandwidth, but not actually using the entire spectrum. So as a starting point, we did a simulation, and in the simulation, we kind of used the same parameters as we later used with the test setup. So we had a sampling frequency of 200 megasamples, center frequency of 6 gigahertz, and a cyclic prefix of 128 samples, and we assumed that all the backscattered signal from the scatterers within our scenario are within that time period of the cyclic prefix to maintain the orthogonality of the OFDM system. And we have an OFDM system in this simulation with 512 subcarriers, from which we can use 400, and the other ones we leave empty. And out of those 400, we selected 30 active carriers, and we had a sparse scenario with like 2 strong scatterers in the scenario, and we assumed that the rest of the signal is buried in noise. And as you can see, this OMP method already works in the simulation, but we want to bring it to the real world. And for the real world, we need a kind of OFDM system first. I know there is several out-of-tree models like the OFDM radar module, but I decided to implement it myself again, so I can tinker with this system and do what I want. So the OFDM system is very simple. So you have an input stream of symbols, you parallelize them, and then you allocate them to the selected subcarriers you want to use. And then you do the IFFT across those subcarriers, and you get your time domain signal. You add a cyclic prefix to this and serialize the signal and send it out into the channel where it's then prone to multipath and noise, and you receive it back at your RX. You parallelize it, you get rid of the cyclic prefix, and you convert it to Fourier domain. And nice feature which is like presented in this relatively old paper from Sturm et al. That you just can do the convolution of your received signal with a send signal, and you get back your range positions. And the nice thing is that OFDM is already a frequency domain modulated system, so we can also do the correlation in the frequency domain by just dividing the initially sent symbols of the received signal. So, this OFDM system I built around the SDR, so I can really stream the samples into real world. And I just did a very basic new radio flow graph with a USRP source and a USRP sink. And I had a vector source and a vector sink, unlike here in this flow graph, but you can also use the vector source and sink, where I then streamed into the data from my OFDM system. And what I didn't know initially is that the TX and the RX are not necessarily in sync. So I added a second RX stream to circumvent that fact and get back my timing delay. So the idea of that, what I did is pictured here. So I send out a chip via the TX of the USRP. So I'm using both daughter boards in my X310, and I send back the signal to the RX1, and I do the convolution, and then I get a timing. And if I do the same on the second channel, and I have the same cable lengths, L1 and L2, on both sides of the power divider, then I can verify that the RX1 and RX2 are actually in time sync when I get the same time delay for both. And I did, so I can use this as a reference. So I just, on one channel, I directly stream in the TX to the RX1, and I use the second RX2 to recover the signal from my scenario. So here's a small setup in my office. So I had the USRP X310 there, and then I sent the signal to the corner reflector and then recovered it back. But actually, this was taken, this picture, before I knew that TX and RX are actually not in sync. So later on for the measurements, I used the cable because I already had returned back that corner reflector to a colleague. And so here are the results of the measurements over that delay line I then used. These are basically the same parameters as before. I have a sampling frequency of 200 megasamples, 6 gigahertz center frequency, 128 sample cyclic prefix, and 512 subcarriers, from which only 30 were active. And the sparsity, since I only had one delay line, was 1 in this case, but it still got back the signal correctly. So the traditional OFDM radar aligns pretty well with the OMP method. And as a future work, I really would like to use the RF knock signals or time signals to convene this two RX channel setup I have. So to synchronize TX and RX, as far as I understood, I could do this using RF knock if I use the replay block and then implement everything with RF knock. That also would give me the possibility to offload some processing to the FPGA and make it real-time capable. So I was really glad to hear that Martin Brown announced that the usage of RF knock is going to be simplified in the future with UHD 4.7. I really look forward to look into this and to make this working. And additionally, like on the long term, I really would like to do use this joint communication system to integrate it into something like SAR imaging. And as a last bullet point, I also have the 410 in my office, but I didn't get it to work at full sample rate yet. But as soon as I do, I will enjoy the enhanced resolution. So thank you for listening, and if there are any questions, I'm happy to answer now or via email later.